Shall we start? Welcome to NPTEL NOC on Point-Set-Topology Part 1. This is maybe the last live session. So today's agenda is to study or introduce you to study of surfaces via quotient spaces through some kind of a game for children in the school do that. So to begin with, recall that in the quotient space constructions we have defined that a Mobius band can be obtained by taking a rectangular piece of paper. So this represents actually I cross, I you may write, but I will write elaborately. So interval 0, 1 cross interval 0, 1, right? And then you identify these two edges. The arrow indicating how you are going to identify. Namely, these points are, you can take it as 0, comma some t, the t range from 0 to 1 will be identified here when you come 1, comma t again. So this will give you the cylinder. On the other hand, same thing if you do, just reversing the arrows by here you can put this way, but here you put the arrow this way. So what is the identification here? T 1 0 comma t going to 1 comma 1 minus t. As t increases here, the corresponding thing will decrease here. This is the Mobius band. So this I am just recalling, this much we have done already. Right now what I want to do is introduce you to the techniques of paper cutting to study these kind of objects. So that is the topics today. So before that, I would like to know whether you have some specific questions in your mind. Also, I would like to take this opportunity to make one small correction also. Okay? So let me see whether you have any questions first of all. So far you have not put any questions. Please go ahead and put some questions. So meanwhile, let me recall you that in module 38, we are studying compact spaces. One of the biggest thing there is to show that compactness is topological invariance. Indeed, it has much more stronger property. Under a continuous map, compact space will go to compact space. That means the image of a continuous image under a continuous map, a compact space, image will be also compact. So this is what we have seen. Then we thought of writing a converse to that, and then this was the theorem here. Namely, take a surjective open mapping. If Y is compact and all the fibers are compact. Fibers means what? Q inverse of singleton Y, where Y ranges over all the points of Y. So all of them must be compact, then X is compact. So this was a theorem there which was used later on to prove that if you have two compact spaces, X and Y compact, then X cross Y is compact. If you grant this theorem, then this theorem comes in a one line proof, because what you have to do is look at just the projection map from here to y or x. So pi y, for example. So fibers will be just x cross singleton y. X cross singleton y homeomorphic to x itself, therefore they are compact. The bottom space y here, that is compact, and pi y is a surjective open mapping. All these things you have, therefore the domain which is x cross y, that is compact. So that will come. Okay, but there is the correction that I want to introduce is this theorem itself is false. So the theorem 3.68 as stated here is false. It can be saved. Now what I am telling is not only the proof is false, the direct theorem is false. So let me first illustrate why this is false by giving you a very simple example, and then I will tell you how to save the entire thing. So that was the right thing which should have been done, that was in my mind, but for lack of time I thought I would take a shortcut, and that shortcut is dangerous. Okay, so let me just show you. So an example here. By the way, so in the screen which you can see now, I have put it in red, added later. So I will make these things available to you in the PDF format, not in the slides. Okay, the slides will be for today's lecture itself, that's all. So why this is a mistake or why this is wrong? So look at this very simple example. There are many examples. Namely, you take from -1 to 1, you don't include both of them. Either include -1 and exclude +1, or include exclude +1 -1. Take the interval and go to 0, 1 via the map x going to x squared. You can easily check that this map is continuous, it is surjection, it is also open. Okay, if you take intervals which are purely contained inside half open 0 to 1 or -1 to 0, then that will be just going to the same open interval here of slightly different length altogether. But even if you take any interval around 0, it will get something like folded, and that is again open inside the closed interval 0, 1. So this is an open mapping. Okay, what are the fibers? Fibers are either singletons or doubletons. So where is singleton? Inverse image of 0 is just 0. Inverse image of 1 is just +1 here, -1 here, +1 is omitted here. Rest of them have exactly 2 points, because y equal to x square has 2 solutions inside that one, that's all. So each of the fiber is compact, right? This is compact, and we know that this is not compact. Okay, so that's an easy example. All right. So the funny thing is, so this shortcut here to this theorem is correct. This is a wonderful theorem. This is very popular theorem also. But the shortcut to prove this one doesn't work. So what is the proof of that? That has to be done exactly as you do the general proof actually, or you can have this proof through what is called as Wallace theorem. Okay, if you go through the Wallace theorem which you have done, or a tube lemma, which is also called tube lemma, then the proof of this one comes very easily, not at all difficult. Okay, so having said that, I will leave rest of them to you. If you have any more questions, you can ask, and then I will wait for a few questions, and then we will start the today's topic, namely coming to the study of these Mobius bands and cylinders. Okay, so that is going to be just a play today. Play and learn. all of you were told to be ready with a piece of paper, a few pieces of papers and a stapler. The paper, what I mean is something like this. Okay. So here what I have done is I have taken some newspaper and here I actually put two staples also so that to make it larger. So this thing is a model for my rectangle here, I cross I, right? So for your school children you can teach that this is a rectangle and what is the quotient that I am taking? I am identifying this edge here with this edge here. There are two different ways essentially of identifying this one. You can bring them back like this together, okay, so that will be with the arrows in the same direction. When you are bringing, you can just make a half twist here and come this way, so that will be the first picture here, wherein the arrows are reversed. So there are two different ways of identifying them. Just to facilitate so that they can put them together, we will make an overlap here like this and put two staplers. Okay, one here, one here. Put two of them, that is essential, I will tell you why. So put them like this. So what you get is the model of a cylinder or an annulus, right? So this is the model for annulus. You can think of this as circle, cross, eye. All these things you have studied. Now you can just think of this as a surface. Okay, whatever. We have not defined those surfaces. Such things will be done only in another course, algebraic topology, which I have already introduced to you. You can have a look at them. That is one of the NOC courses. Okay, so both of them right now, along with me, you can perform. Okay, please carry on and have some models for yourself. So that is the game today. So I take a strip like this, go straight forward. Without twisting, you join them, put two of them, two staplers. So that is a model for cylinder. Okay. On the other hand, if I make a twist, then what I get is, so take same thing like this, but before joining them, make a half twist. Interchange the directions, the arrows. Put two staplers. And that is called Mobius band. So have them in your hand, okay, both of them. Do you all have them? So now I ask you the following question. Please listen carefully. Look at the cylinder, how many edges it has? How many edges it has? The same question, look at the Mobius band, how many edges it has? Okay, so there are certain geometric things that you can talk about, like when you have a triangle, you know what are the edges. A triangle has three edges, right? Now we are trying to do things which are not just plane figures, but this is not a plane figure. See, it is inside a three-dimensional space. But what is common? It is still a two-dimensional space. The space is two-dimensional. So that is where topology enters in, but keeping a lot of geometry still. So what are the edges? What are the boundaries here? How many boundaries are there? How many means what? So these are the fundamental questions you have to answer in terms of ordinary English which the people understand, but you have to convert it into precise mathematical definitions, right? So before that, answer these questions without bothering about the definition. How many edges does it have? Okay, and then look at this one. This has some inside here and an outside here, right? So there is an inside here and there is an outside here, in the sense that if some ant is here, it cannot go to this side unless it crosses the edges. Somewhere it has to cross the edge. So there are two sides here. The same question, how many sides this has? Okay, suppose you have an ant here, can it go to the other side without crossing these edges, without any touching the edges at all? So these are the questions, right? So answer them, find out your answers, very easy. If you respond, that's very good. So let me see whether you have anybody has responded. Yeah, Swarupal says cylinder has two edges and the Mobius band has only one edge. Okay. So many of you may agree, right? Do you all agree, or anybody has a different answer? You would like to know. Meanwhile, make a few more copies of these things. 2 cylinders, maybe 2 or 3 Mobius band and so on. Okay. Okay, now comes the next question. Suppose you cut this cylinder right in the middle, across this way, not this way. Don't cut this way, but right in the middle along the circle like this. Cut it. Make one single cut. When you make cut means what now? So you see, all these things you can mathematically define also. When you cut it, how many pieces you get? And what are those pieces? Are they just piece of paper, or are they some models of some mathematical objects here? So that is the first question. The second question is the same question for the Mobius band. So if you cut along the central circle here, how many pieces you get? And what are those pieces? Okay, think about that. If you have some answers, please feel free to respond in the chat section. One of the things I want to tell you is that you should not, though you have the Mobius bands in your hand, you should not cut it yet. I have only to, if you cut, what you get. Okay. So that should be answered just by thought process only. Then only you will learn something. All right. So get your answer, check it, and think about it, whether there may be a different answer, think about it, and then only you can use a scissor and cut it. Okay. So there is one answer here. If you cut the cylinder along the central circle here, then you will get two different cylinders of smaller size, of course. The size doesn't matter here, they are cylinders. Okay. Not only that, you can hold one in one hand and the other one in another hand, or you can post one of them to me and keep it, the other one you can keep it at your home. So such a thing is possible. Okay. So there are two copies of the same cylinder if you cut it in the center. Okay. But what about the Mobius band? First, answer how many pieces will be there first of all. Then how many pieces, and each of the pieces how many, what they are. There are two parts of this question. Okay. In the day-to-day language, when you cut some piece, you must at least get two pieces. But a single cut can achieve, you can get many pieces also by one single stroke also in certain situations. But here is a situation wherein a cut in an ordinary sense may not mean what you expect, namely you may not get two pieces. So that is the whole idea here. Okay, and how to explain this behavior. So that is the mathematics behind it. Okay, so again Swarup Pal is the only one who is responding. If we cut the Mobius band, then we get a band with two twists, he says. So he has already answered one part, namely there is only one band. Okay, you can talk about this also as a band and this is a Mobius band. But both of them are band, but which one is the band now? So, okay. So what is the meaning of two twists? There are only two objects topologically. Either it is the Mobius band or it is the cylinder. So which one are you getting? So that is the question. Okay. For example, you can again ask how many edges the new object has, how many sides the new object has. So that is a fundamental question whenever you have this kind of an object. First thing is to check how many edges it has, how many borders it has, right? The second object is to check how many sides it has. Are they always go hand in hand? The two sides are there and then two edges are there for the cylinder. For the Mobius band, you have not yet answered how many sides it has. So the Mobius band has only one side. What is the meaning of one side? If somebody is, say, on this side, as a mathematical object, there is only one point, whether this point where you look it from this side or this side, if you have transparent thing like this. But as a model inside R3, okay, this has locally two sides. That means what, in your elementary surface theory, in your calculus course, you can take the surface and take a normal, take a perpendicular to the surface. That perpendicular has two different directions at each point. You can say one is this way, one is that way, but what is inside, outside, I don't know. Okay, there are two perpendiculars, right? If you have a circle, at any point, there are two perpendiculars to a circle. There you can easily talk about inside and outside. So at each point, I can draw two perpendiculars, right? So that is a tangent, and that is the normal. So normal has two directions. Okay. However, so that will tell you at each point you have two sides, but the global side, all over, it has only one side. What is the meaning of this? For example, if you look at this normal, start moving the point, don't make any abrupt changes in the normal. Start moving this point. Okay, then what happens? You will start moving this way. For example, you come here. So the normal will be still like this way. Okay, I am looking at this normal. Let me put a different color here. Okay. So keep moving. So what happens? Keep moving. What happens? Don't make any abrupt changes. When you come back, you will come back to the point, you would have come back to the same normal, not the other normal. This phenomena is exactly the opposite if you take the Mobius band. You hold your, put a coin, for example, instead of a normal, and move it around. When you come back to the point, the coin will be on the other side. The same point on this band, okay, but it will be on the other side. It will not be on this side. So what happens is, here it doesn't happen, but when you go around, come back, it will be this normal for the Mobius band. This you can check. Okay. So that is what is known as a non-orientable surface. Whereas this will not happen with what? With the cylinder. Okay, cylinder is called an orientable surface, whereas this is an example of an orientable surface, like many other objects inside R3, whereas the Mobius band is one single thing which is called a non-orientable surface. Okay, so it has only one side. You can paint this one side completely red, and the other side, say, you can keep it blank or put a black color. Okay, one is a white color, black color. So that kind of work will not be possible with this one. You start painting on one side, keep painting, extending wherever you see the blank. By the time you finish, both the sides, the so-called both the sides, which way there are no two sides, both of them will get painted. Locally there are two sides. So you will have paints on both sides. That's the point. So this is the property of the Mobius band. Now go back. When you cut a Mobius band, along the center line. What is that object you are getting? So Swarup says it is a band with two twists. I have not introduced that one because if you start with a piece of paper, you don't twist at all, come and join it, you get a cylinder. You make half twist I am telling you, okay, not one twist, half twist, you get the Mobius band. If you make one full twist, namely 2 pi, then the arrows are the same. Therefore, what you get is the same topological object. Arrows will have the same direction, they will coincide. So identification is only this one. So this description of whatever the quotient space you are getting, that does not involve this operation of twisting. How many times you might have twisted, it doesn't bother. All that it bothers is when you are identifying whether the arrows are matching or arrows are reversed. Okay, there are only two cases. So accordingly, there will be either a cylinder or a Mobius band. So in this perspective, you must answer what is the object that you have got after cutting the Mobius band. So the process of getting this one is not exactly the same as what we have done, but if you go back, for example, if you take the cylinder, if you take that object, cut it across means what? Across one of these lines like this. Okay, then what you get is a strip of paper only. Therefore, the object which you have got in your hand without cutting should be one of these two. It cannot be something else. So you have to tell me which one it is, whether it is a cylinder or a Mobius band. Okay, there cannot be anything else. So this is where common intuition may fail, but having learned topology all this while, you should be able to do some abstract thinking which will tell you exactly what happens. Okay, the first thing is I will tell you why the object after cutting the central line here, cutting means what? Just remove the center line here, okay. So whatever object you have, it is only one. What is the meaning of that one? One object, what is the meaning of that? Is it only one atom? There are uncountably many atoms here, right? So what is the meaning of that? The whole space is connected, path connected. So that is the idea. Okay, when you say one piece, it's number of components, path components. So that is the meaning of this one piece, two piece and so on. That's what geometrically, that is the meaning of that one. So path connectivity is the one which we are using here. So I want to show that this whole thing is path connected, that we know, because what? Start with the rectangle is path connected, and this quotient space is path connected. But when you throw away a line, is it path connected? All that I will do is, I will not use this model, but I will use this mathematical model here, mathematics here, directly. So what is the image of, what is the central circle here? When you come to this picture, in this picture, the central circle will be the image of this line, the central line here, the central line here. What is this? This is the entire I cross 1 by 2. right? That's center line. So cutting along that means you throw away that part from your space and then look at the remaining thing. So what happens? Here it is a line segment. When you identify this edge with this edge, the corresponding 0, half here will go to 1, half. So these 2 points get identified, and that we know is a circle. So that is the circle you are throwing away from the quotient space, which is the same thing as first you throw away this one, this line here, and then do the identification. So if you do it for Mobius band, what you get is 2 different portions here, and both of them are getting identified on separately. So that's why you are getting 2 different cylinders. The same thing which you come here, what happens? When you throw away, you have 2 different objects. But how is the identification taking place? Look at this arrow. This arrow here now has cut into 2 arrows, right? So I have to write like 2 arrows here. So one arrow is like this, another one is. So corresponding arrow here will be this one now. It has gone up. So this arrow gets identified with this one. This portion here, the red, let me put a red portion here. This portion here gets identified with this portion. Okay. In other words, what is happening is the following picture now. You have 2 different pieces of paper. After throwing away this half line, you have 2 different pieces of paper. So I will draw it somewhere here, the second part. Okay? So I can just shifted the lower part here. Now look at this line here, double arrow here. This is getting identified with what? You see the double line here on this side. Twist it and put it this way. Okay, that's what you have to do. So instead of drawing like this, I can draw this way. Only thing is, this is twisted here. So what has happened to this line here? This line, look at this one, this is downward arrow here, right? This downward arrow here. But I have to identify it with this one because this is upward and that's downward. To make it downward, I have to turn it around. When I turn it around, this arrow becomes this way. Okay, what is the red arrow here? The red arrow here is standing upwards only. So now I have a larger piece of paper. I have yet to identify a part, namely this edge has to be identified that way. How? With the arrows in the same, coinciding, the same direction. So when I do that, what I am doing is this operation, which is an ordinary cylinder, right? Okay, so in conclusion what I have is, when I cut the Mobius band along the center, what I get is one single object which is nothing but the cylinder. However, the actual practice, when you actually cut it and look at the object there, it is what Swarup is telling me, namely a band with 2 twists. It is not a band with 2 twists, I want to correct it. It is again a cylinder, but while bringing here you have forgotten, you travel is too long and so on, you come back like this and put it this way. So there is one full twist inside that one. Okay, topologically it is the cylinder, but the way it is embedded in R3, that is different. It has got twists. So even these twists, etc., twists and turns and all that can be mathematically explained properly. Okay, so each of them becomes, interesting objects, namely knots and links and so on. All right, now I allow you to actually cut it. take your Mobius band, cut it along the central circle and see what exactly you get. Okay. Some of you might have already done it because you are curious. So that is what you get, one single object. How many edges does it have and how many sides it has, all these things you can check. I don't have to check because I have already proved that this is cylinder and it must have two sides and it must have two edges. So you can check that. Okay. Now what you would like to do is you put two more staplers there for the object that you have got like this. Put one more stapler, we have put only two staplers, so put one more stapler there so that we can do something more on this one. Now, this is a cylinder, right? Now cut it along the center line here. When you cut the center line, a cylinder, you know the answer, namely you will get two cylinders. All right. The point is whether you can keep one cylinder at your home and send the other cylinder to your friend. Can you do that? Is the question. So before cutting, you should first answer the question, to yourself at least. If not, you are not coming and answering me in the chat. At least answer to yourself and then cut it and see what you get. Okay? This is one question. The second question is, for those who are a bit quick, take a Mobius band. Once more, see, that's why I told you to make a number of copies of the Mobius band. Okay, if you haven't got it, so you'll have to make it. So take the Mobius band again. This time, don't cut it along the center, but slightly away from center. Okay, so somewhere slightly nearer the edge, you make a cut. Go on cutting. Okay, don't cut across. When you cut across, you will get only a piece of paper, rectangle piece. So do cut it. So what is the result of that cutting? Will you get one single object again, just like the case wherein you cut it in the center line? Or will you get two objects, or maybe more? So that is the question. cuttings, twistings, all these things are interrelated. One can do a systematic study of these things as a part of what one knows as, what is known nowadays as, links and knots. There is a lot of mathematics in that. So finally, I would like to have one more demonstration here. Without explanation, I would let you think about it only. So when you cut a Mobius band off the line, off the center, what do you get? So Swaroop has answered something. If you cut along a line other than the center, we end up with two Mobius bands entangled with each other. So finally, so far all his answers were correct, but this time he is wrong. Partly wrong. If you cut a Mobius band along a line, along, a line or circle, whatever, off the center, okay, on one side of the center, what you will get is two objects, yes. The inner part, which is not disturbed, that will be a Mobius band itself. The outer part, okay, with the thinner part, that will be what? A cylinder with one full twist. Okay, and they will be entangled also. Similarly, if you take a cylinder with a twist, and if you cut it, you will of course get two different cylinders, but they will be again entangled. Entangled means what? They are linked in a non-trivial way. So that is why you won't be able to send one of them to me and keep the other one at your home. That is the meaning of that. They are entangled. What is the meaning of entangled? We have to express that. So that is a big branch of mathematics, big branch of topology called links. Okay, knots and links. So here I would like to have demonstration. I will need somebody help. I need some volunteer. Where is madam? Just like you have helped me last time. Yeah. You can keep your mobile here. So hold this one. Hold it just like that. Hold it. Like this. Yeah. So like this you are holding, okay? Yeah. So hold it. Hold it together. Just hold it like that. Here again, on this side, hold it, hold it. Just show me. Hold it. You have to hold, sorry. You have to hold it like this, like that, Okay. No, I am not confused. No, this is not correct. See, I wanted it to hold like this. So how? No, okay, it's very important. Hold it now. Now shake it out like this. Shake it out. Shake it out. Over. You see, there are how many twists are here, and how many twists are here. See?
This is different and this is different.
That's different. There were many different ways of doing it. All that I am doing is going around twice, but while identifying I am doing different. That's all. So this is what I wanted to tell you. So turning and twisting, they are interrelated in a very complicated way, but that can be expressed mathematically. So that's what I wanted to show. So I would like to show you again one more of the same thing, that there is no cheating or anything. This is all mathematics. It's not magic. So just hold it. Hold like whatever. This I should see like that. Okay. I'm looking at the other way around. One second, It's not coming correctly somehow. See, I should want to say, this is the way you have to hold. You see, that's very simple, but you have to hold it correctly, that's all. See, I can face it like this, right? So now touch twisting like this and folding. That's all. Now the same thing I am doing here. Just hold it like this so that I can, that's it. 1, 2, and I'm just hold it. Now shake it out. There are no twists at all now here. And here there is still one full twist. I can make half twists, 2 twists, 3 twists, any number of them. See, there are no twists at all here. So think about this. That's it. Thank you, madam. Thank you. You can keep it there. Yeah. So, any questions, Swarupa? Okay, if there are no questions, thank you all for participating. I hope you have enjoyed this course. This is perhaps the last live session for this course. Soon the course will end. This is the last. Some more questions? It's only part of the question. I could not see that full thing. Can you show the full question, because it's full here? The question is,
So he wants to draw it and explain it. He's asking, can you once draw and explain the part where we are cutting along some line?
his question, whatever, it's cut off.
Draw it.
Huh?
He wants you to draw it and explain it. Draw it on the board and explain.
Where is the question? Can you show me? See, on that one, it's only half, it is not fully appearing.
So this one.
What is the question? Can you read?
Can you once draw and explain the part where we are cutting along some line?
Yeah, that's where he made a mistake. Okay. Good question. So here is the proof. You have the Mobius band, you can perform it and verify, but here is the proof. So let me draw a different picture here. So this is the Mobius band with an arrow here and the arrow here this way, right? Now I am cutting it, say at 1/3 line instead of 1/2 here, at 1/3. Okay, you go on cutting like this. So this, what is this point here? This is 0, 1/3, right? What is this point here? It is 1, 1/3. 1, 1/3 in this picture appears again here because these 2 points are identified. 1, 2/3 will be identified with 1, 1/3. Not 0, 2/3 will be identified with 1, 1/3. These 2 points are not identified, right? That is the identification here. 0, t identifying with 1 minus 1, 1 minus t. So if I take here 0, 2/3, that would be getting identified with this point. So when I am here, it is same thing as I am here. So I have to keep going further. And what do I come here? This is again 1, 2/3. And what is that? That is identified with this point, the starting point. So starting from here, I will be traversing twice the distance to come back here. So now I have completed one single cut on the Mobius band. Okay. When you cut it, what happens? The central part here, this arrow is getting identified with that arrow, the smaller arrow. Only the size is different. The arrows are reversed. So this portion remains intact. And what is the image? That is the Mobius band. What happens to the cutout part? That is an ordinary cylinder now. You can see that, which I have explained earlier also. You see? So you can take this one as different portion here, a different strip here, put it here. Okay, you have to make a twist, and then what you identify is just ordinary identification. Okay, so the two objects have explained. All right, how they are entangled, that is more difficult to explain on just this board. That can also be explained. Okay. So, thanks for this question. This is a method now. You know, whenever you want to study the quotient spaces, if you have difficulty what is happening there, come back to the mother space, the original space, and understand what is going on there, and then go back. Okay? Thank you. Any more queries? I can't see them because this is full now. Okay, that's fine. Yeah, that's fine. So thank you all. Best of luck. Hope we will meet you in the second course, second part of this setup.